Think about the peak of modern human achievement. We can image the event horizons of black holes. We can rebuild human faces through complex surgery. We route endless streams of digital code to satellite networks orbiting the planet. It is easy to look at these marvels and assume they are the exclusive products of a 19th century European scientific awakening. Yet if you trace the logic powering these breakthroughs, the calculus used to model gravity, the radio waves connecting our devices, the concept of zero, and the actual mechanics of surgical reconstruction, the origin point is much older. These concepts converge in the Indian subcontinent, part of a continuous intellectual lineage spanning from 600 BCE straight through to the modern space age. To see how we arrived at our high-tech present, we are going to explore three core pillars of modern science, each pioneered by Indian visionaries whose work continues to influence almost every piece of technology we use today. These roots show that the tools of the modern age, from coding to surgery, have been developing across continents for millennia. Innovation is a shared global inheritance. Let's start with the most essential tool in mathematics, zero. Before it was a number, nothingness was largely a philosophical concept. Translating the idea of nothing into a mathematical placeholder completely reordered how human beings trade, calculate, and build. In the 5th and 7th centuries, mathematicians like Aryabhatta and Brahmagupta gave this concept formal rules. They established the modern numeral system and figured out exactly how to compute with zero. Brahmagupta pushed even further into algebra. In his main treatise, he recorded the first clear description of the quadratic formula. He figured out the general solution for equations with unknown variables, laying the groundwork for modern algebraic math. 700 years later, in 14th century Kerala, another mathematical leap occurred through a scholar named Madhava of Sangamagrama. Madhava discovered infinite series, the ability to add an endless sequence of numbers to get a finite value. He developed accurate power series expansions for trigonometric functions like sine and cosine, making him the founder of mathematical analysis centuries before Newton and Leibniz formalized calculus. This mathematical intuition carried into the 20th century with Srinivasa Ramanujan. Growing up in Tamil Nadu with almost no formal resources, he spent his early 20s working as a grade 4 accounting clerk in Madras, solving complex equations on packing paper in his spare time. His unrefined brilliance caught the attention of scholars in England, eventually bringing him to Trinity College, Cambridge. Here, the self-taught clerk collaborated with some of the most highly trained mathematicians in the world. He saw relationships between numbers that no one else could. When a colleague mentioned arriving in a taxi with a boring number, 1729, Ramanujan instantly replied that it was the smallest number expressible as the sum of two cubes in two different ways. His most advanced work emerged in his final days, where he developed Mach theta functions. At the time, these functions were disconnected from known physics. Yet today, a full century later, theoretical physicists use Ramanujan's exact equations to calculate the entropy inside black holes. Moving from abstract mathematics to the physical mechanics of the human body requires us to rewind to the ancient city of Kashi around 600 BCE. Here lived a surgeon named Sushruta. He compiled the Sushruta Samhita, an encyclopedic medical thesis detailing over 1,000 illnesses, human embryology, and the precise management of fractures and surgical extractions. His most significant work involved early reconstructive surgery. Sushruta developed a method for rebuilding a damaged nose by cutting and rotating a flap of skin from the patient's cheek. He achieved this with custom instruments he designed himself. He insisted on practicing incisions on cadavers to master anatomy, and he emphasized strict cleanliness and sterilization thousands of years before the discovery of germ theory. By the late 19th century in Calcutta, this deep curiosity about living systems expanded into the broader natural world through the polymath Jagadish Chandra Bose. Bose designed sensitive instruments to measure plant responses. He proved that flora possess an internal nervous system that actively reacts to environmental stimuli. Bose was also a physicist. While experimenting with how electricity moves through materials, he anticipated the existence of p-type and n-type semiconductors. the components that control electrical current in every modern microchip. He took this further by conducting research into radio waves in the microwave spectrum. He used semiconductor junctions to detect these waves and invented the mercury coherer, a device capable of receiving radio signals across distances. Bose's early manipulation of microwave optics provided the physical foundation for the wireless technologies we rely on today. Without those experiments, modern radar, global telecommunications networks, and Wi-Fi would not exist. Around that same era, another physicist was unlocking the secrets of light, Sir C.V. Raman. Raman discovered that when light passes through a transparent material, a small fraction of the light is deflected. More importantly, that scattered light changes its wavelength. This phenomenon, known as the Raman effect, allows us to analyze the molecular structure of liquids and gases. His documentation of this light scattering earned him the 1930 Nobel Prize in Physics, making him the first Asian individual to receive a Nobel in the sciences. Following India's independence in 1947, this legacy of theoretical physics evolved into applied engineering under Dr. Vikram Sarabhai. Convinced that advanced technology was essential for a developing nation to thrive, Sarabhai successfully established the physical infrastructure that would eventually become the Indian Space Research Organization, or ISRO. By 1975, this institutional effort culminated in the launch of India's first satellite, appropriately named Aryabhata. Working alongside Sarabhai was an aeronautical engineer named Dr. APJ Abdul Kalam. Kalam spent 2 decades mastering the composite materials and propulsion physics required to get heavy payloads into orbit. He served as the project director for the SLV-3, India's first indigenous satellite launch vehicle. He then applied that mastery of rocketry to national defense, leading the development of the Agni and Prithvi missile systems. Sarabhai and Kalam built a domestic infrastructure of scientists, launch pads, and mission control centers. They proved that a newly independent nation could achieve self-reliance and operate at the highest tiers of aerospace engineering. Our digital and physical landscape grew from a global blueprint. We can track the logic of Sushruta's ancient scalpel through the mathematical manuscripts of Madhava and ultimately into the orbital trajectories calculated by Kalam's aerospace teams. These breakthroughs were won against deep structural and societal barriers. Srinivasa Ramanujan lacked formal resources and battled a fatal illness, yet he managed to outline the mathematical geometry of the universe from a hospital bed. Jagadish Chandra Bose pioneered semiconductor physics and wireless optics under the weight of colonial and racial discrimination. And engineers like Sarabhai and Kalam managed to kickstart a world-class space program from scratch within the tight economic realities of a newly independent country. True scientific vision operates without borders. These pioneers proved that even with limited resources and immense pressure, a single insight can change human history.